So the purpose of this webinar is to deliver the understanding of VSM, value stream mapping tool, and its application. The objectives, I'll try to stay focused around defining VSM and where and when to apply VSM, some common terminology that we use, the symbols in VSM, and again, as I said before, I'll walk you through an example to apply VSM on. Special type of flow charting tool that is valuable for the development of lean processes. It's got, and again, this is maybe different depending on where you're applying VSM, but most commonly we use two-part process. The current state of the process and the future state, the possible future state of the process. So what would be the benefits? Based on the experience that I have gained over the years, VSM helps to reduce the cost. And I'm not going to talk about how and why, where it does that. When we, at the end, when I walk you through the example, we'll pinpoint how it's going to actually showcase the cost reduction there. Next one is reduce the lead time. To me, lead time is one of the key output of VSM. And technically, if you reduce your lead time, you're going to find out that everything else that I'm going to be talking about here as part of benefits can be affected by that. Third one is increase the value added time. Well, then decrease non-value added time. Next one is it will allow us to identify sources of waste in the value stream. And of course, by doing that, we will have an improved decision-making process. And as I was pointing out, VSM will also allow us to create a common language that all employees understand through the use of standard VSM symbols. It will provide a way for employees to identify and eliminate areas of waste. And finally, this is one of the key tools that will allow us to showcase the linkage between the information flow and the material flow. So what are the value and waste identifications? Value is that for the sake of which a process exists, for example, to produce designs that meet the customer needs within the constraints of time, money, and regulatory requirements. Waste in a process is anything not needed to get the job done to the satisfaction of the customer and other stakeholders. Most common waste and losses are the transportation. This is when we're moving people, products, and information. Next one is inventory. This is when we store parts, pieces, documentation ahead of requirements. Third one is motion. Motion is when when someone is bending, turning, reaching, and lifting anything related to the operations. Fourth one is called waiting. Waiting for parts, information, instructions, equipment could be categorized under waiting. Fifth one is overproduction. Overproduction is making more than required or needed. Next one is overprocessing. This one is like, for example, tighter tolerances or higher grade materials than are necessary. And a good example of that would be inspecting a defect visually versus putting that through an X-ray. So next one is defects. Any rework, scrap, incorrect documentation could be categorized as defect. There's one more that's not here that's been commonly used recently. Is called skills. That skills usually considers the underutilizing capabilities, delegating tasks with inadequate training would be treated as skills. So the way I actually color coded these common wastes with skills, if you were to read the blue words, I mean the blue letters, I go by Tim Woods. So if anybody wants to try to memorize what these common wastes are, just go by Tim Woods. The waste identifications. So this is actually when we do have face-to-face, when we do the training, this is a good actually discussion point. So kind of points out the inventory, any finished product waiting to be sent, any work in process, and raw material. They all are considered to be inventory. Overproduction, producing more than necessary. Overprocessing, processing anything longer than necessary or making something complicated than it's necessary. Transportation, movement of product by machine, people concerned with layout and flow. Motion as a form of waste, any movement the person makes. Defects, all products or services rejected, rework or scrap, and incorrect information. And some places that I worked or I worked with, they also consider retesting as their defects. Waiting, again, spend time on maintenance to come out, do PM, or material shortage, machine downtime, or you need engineering support. It's all, again, considered to be waiting, and it again, it's a non-value added. So some of the resolutions to waste identified with VSM. So now we're going to look at some of these common wastes. Overproduction. One of the best ways to resolve that is actually a pull or Kanban system. It's not part of this this webinar, but pull or the Kanban system is very commonly used to, again, manage the customer demand requirements. The bottleneck. The best way to eliminate bottleneck would be a line balancing. Transportation, I think the best way to, again, minimize the transportation or optimize the transportation would be to use the material flow planner. Layout, we could use the concept called cellular manufacturing to optimize the layout. And long lead time, we could utilize the pull or single piece flow to minimize the lead time. Information flow, of course, communications. Functional layout is also another cellular layout concept, can help us to come up with a better functional layout. Batch flow or inventory, similar to overproduction, can be taken care of utilizing pull or Kanban system. And defects, how can I come up with zero defect concept? This is when we deal with the quality at the sources. So when do we use VSM? We need to use VSM in a high volume production environment, low variety product mixes with the few components and sub-assemblies and dedicated equipment. So if the question is, what if I have low volume? Well, I guess you're not going to get the best out of. You can still utilize, of course, VSM, but you're not going to get the best results out of that. And if you have, again, very high variety of product mixes, then the unknowns are going to be huge. The scope is going to become almost, again, depending on how high variative product mixes that you're dealing with. But the scope can be so large that can lead to unmanageable VSM activity. So how do we develop a VSM? Excuse me. As I pointed out before, we have two parts of processes. First, what we do is we depict the current state of the process as is. From there, we come up with a possible future state. And again, as I was saying earlier before, others may use the third option. They call it ideal state. To me, I tend to not to use that state just because we don't tend to know what ideal state is most of the times. For that reason, and even if we do, we know that reaching the ideal state. I mean, using it as a goal is fine, but reaching that goal seems to be very, very much challenging. So for that reason, I would rather stay focused on a future state, a possible future state that team can come up with based on the current state. So a current state map shows work processes as they currently exist. This is vital, both to understand the need for change and understand where opportunities are. And finally, while value stream maps appear complex, their construction is easy when taken in a logical step. So as I was saying before, when we are developing VSM, we use symbols that are somewhat standardized and categorized as process, material, information, and general symbols. And here are some of those symbols that we commonly use. As you can see here, we have process symbols for customer and supplier. We have a process symbol, data box that we always use it along with the process box. Work cell layout symbol, operator. As far as the materials, we have two symbols that we commonly use for the inventory. Shipments in and out, Kanban stock point, material pool, safety stock, external shipment. As for the information symbols, we have production control, where central control point. There is a daily or manual info. That's what this straight line arrow is. The monthly electronic info is the like a lightning type of arrow. And then the general symbols, we use Kaizen burst for the opportunities that we identify as an improvement opportunity. And finally, we use the NVA and VA, which is the which kind of defines the lead time from beginning until the end. So here's an example that I want to walk you through. The company XYZ Manufacturing, two different valve sleeves that have the part numbers, let's remember 4 and 6. Few slides, I'll demonstrate how to develop VSM for these two products. Now, the first step we do is to draw the outbound shipping icon and truck with delivery frequency. So that's my production control. And my first step is my shipping, right? A shipping icon and truck with delivery. So now, we're going in VSM, we go backward. So please keep that in mind. So we're going to ship to our customer. As you can see in the truck, it says daily. And the quantity here is given as we're going to ship on a daily basis, a little bit over 10,000 pieces per month. Sorry, 10,000 pieces per month. On a daily basis, we're going to ship about 500 per day. And it also provides you the mixture between the two parts, 4 and 6, if you remember. And those are equivalent to these right here, 500 parts are equivalent to 12 containers per day. So why do I need to know that? That's specific because that's going to define the size of truck or number of trucks you're going to need to use to ship your products out. The second step is drawing the inbound shipping icon, truck, and delivery frequency. So here we go. Now I have my inbound. That means, okay, in order for me to produce a part and ship them to my customer, I need to receive raw materials. And again, in the current state, we receive parts from our suppliers on a weekly basis. Please pay attention to the time difference between receiving and the shipping. Okay, so what's third step? Third step now is that we're going to have to add process boxes in sequence from left to right. So I received my raw material. So what are my process steps that these raw materials will go through to produce these valve sleeves? Okay, so apparently the first step when we receive them, they go through machining operation. From there, it goes into a honing operation. From honing, it goes into cleaning and deburring and inspection. After that, packaging. So in other words, we have 5 process steps that the raw materials go through, and we have a final product at the end of clean and debur, but then we clean it up and then we pack them and ship them to our customer. So those are the processes. So fourth step is then, if you remember, I mentioned earlier when I was talking about the symbols, the process boxes are accompanied with the data boxes. So we're going to add data boxes, including value-added and non-value-added item timeline below. So here we go. I have all my data boxes. I haven't decided what kind of data to include, but I know that I have to describe each process. So that's step 5. And please also pay attention to this right here is when we said, remember, NVA, VA, non-value-added, value-added, non-value-added, value-added. So processes that the parts are going through are considered to be value-added. Anytime in between the process, they are non-value-added. So the next step, another one before we talk about the next step, keep in mind that the communication now between the production control and the production supervisor will have to take place. So for that reason, we define the communication arrows. Okay, so my production control sends the production supervisor what to produce at what quantity on a weekly basis. Then production control sends the forecast to the suppliers, but then orders weekly, as we defined it already in the receiving icon. And the customer actually sends our company monthly forecast, and they also order weekly. Then based on that information, so the production supervisor will have to communicate with each process step on a daily basis to determine what they are, how many they're going to be working on. So before we go to the next step again, another step that we need to complete here is to define or add the operators for each of the processes. As you can see, the operator symbol is included. The one that has like a stripe through here, That's because, as you can see, it's not a person, it's a portion of a person. In other words, it's a person that's borrowed for a small amount of time on a given shift. So we have so far 3 dedicated, 1 shared resource, and actually 4 dedicated. Then we need to, again, add the process attributes. So for each of these processes, if you remember, the boxes, the right data boxes. So we're adding cycle time, operator time, equipment time, changeover time, if any, the lot size, availability per shift in minutes, and uptime in percent. So now that once we add all that information for every process of the way, the next step then becomes we need to add the inventory locations and their levels. Well, let's add them up here. Okay, now the inventory, first inventory. So we received the raw material from the supplier, and we have 5,500 of them in inventory every given point of time. In between the machining and honing operation, we have a mixture of 3,360 versus 1,680. And in between honing and cleaning or deburring, there is 3,500 pieces in inventory. Between cleaning and inspection, we have 2,000. Inspection and packaging, we have 2,000. As the finished, we have 2,000. So the next step, sorry, let me take you back. So that's now that I have pretty much everything I need, plus I'm gonna need to add the working hours, and it's here in this box. 1 shift per day and 8.5 hours, where half hour is lunch, half hour is breaks. So available time is 460 minutes. Cycle time and lead times. So they're added in here. So we have 11.9 days worth of inventory. That's this amount right here. And the cycle time of machining process is only 44 seconds. Then between the machining and honing, we have 10 days of inventory. Then the honing operation is only 40 seconds. Then between honing and cleaning or deburring, we have 3,500, which is 7 days worth of material for 5 seconds of operation, cleaning and deburring operation. Between cleaning and deburring, we have 2,000, which is 4 days worth of material, when inspection takes only 30 seconds. Between inspection and packaging, we have 4 days worth of material, when packaging is only 10 seconds. And then we also have 4 days worth of finished product to be shipped. So the next step is to calculate the total cycle and the lead time. Well, based on this information right here, it's really easy to calculate. As you can see here, all I have to do is just add all these up to calculate the lead time. So lead time is, again, pretty much 11.9 days plus 44 seconds, 10 days plus 40 seconds plus 7 days. That gives us about 41 days. When the process time are the sum of these process times, right? 44, 45, 30, 10, only a little bit over 2 minutes. So for a 2 minutes of process time of operations, we have 41 days worth of inventory. Think about the cost of that. So this is a cheat sheet that I put together here usually that again walks you through the steps that we just calculated. Now the Okay, so that's when that's how we develop a current state. So based on the waste that we talked about and resolution methods with those waste, now we could use some of these techniques to come up with some opportunities for improvement in the current state. And the future state will help with the larger process of developing your lean manufacturing strategy. It requires significant knowledge of core disciplines and other specific topics. Designing a future state requires more art, engineering, and strategy than present state mapping. Understanding the following subjects will help define better future state map. Again, cellular manufacturing that we pointed out in the resolution methods. Next one is the takt time. Next one is Kanban. Setup reduction. Implementing Kaizen, group technology, lot sizing, and that's that. So as you can see, again, of course, these are not the full list of tools that we can use to make improvements on or help define future state opportunities. But these are very key topics to know more about before, again, you can come up with a better future state. So starts with the calculating the takt time. The calc time is the average time between production units necessary to meet the customer demand. So we use this formula for that. And in this case, if you remember, we had the net available time per shift was 460 days, and customer demand per shift was 504 pieces per day. So technically, my takt time is 55 seconds. So if I can produce a part every 55 seconds, that means I'm meeting my customer requirement. So, okay, so that's this box right here. So we defined what the takt time is. Next one is that we're going to look at the bottleneck opportunities. So if you remember, we had machining that was 44 seconds, honing was 40, cleaning, deburring was only 5 seconds, inspection was 30, and packaging was 10 seconds. When the takt time was 55 seconds. So there's a lot of non-value added time for each of the process. So what does that mean? So against this, we don't have a bottleneck technically because every one of these processes are less than your takt time. So now identifying the lot sizing setup opportunities. So this one usually the present lot size was 1,000 pieces, about 2 days production. This requires at least 3 to 6 days finished goods and prevents daily adjustments to mix or demand. Now, if the lot size were simply cut, it would allow faster response, but additional setup time in machining would use available time. Machining could not meet the average customer requirements. However, if a focused setup reduction is made on machining and setup becomes 20-30 minutes, a batch size of 500 or even 250 is feasible. So the mapping team established this as a goal by a Kaizen burst, as you can see it here. So we're first focusing on going from 1,000 to 250. And the setup times on the first one was 60 minutes, and the rest were very negligible. So again, there's an opportunity here to reduce the setup time on machining. The balance chart shows the cycle time for each of the 5 process steps. Machining and honing operations are closely balanced. Cycle times for clean, deburr, inspection, and packaging are quite short in comparison, as you can see. The very short cycle times for clean, deburr, and packaging indicate low utilization in a cell. However, inspection and packaging are manual operations that require little more than a workbench and hand tools. High equipment utilization is not critical. Clean deburr process is run on a specialized equipment in a central area. If clean deburr can be scaled down as a manual or semi-manual operation, it can go in the cell. This seems feasible and the team accepts that. So it will be done. It appears that 3 operators can run the cell. This is not a precise calculation though. It only considers present cycle times and ignores setup. So work cells are more involved than suggested here. However, our purpose is not to finalize the details, but make reasonable suggestions. So with a work cell for 5 processes, scheduling between them becomes a trivial case. They will be directly linked with continuous or small batch flow. Kanban internal to the cell is unnecessary or becomes part of the detailed cell design. Kanban does apply at 2 other locations, between cell and the supplier, between cell and customer. The detailed design of the Kanban systems, as you can see here, are shown in the Kaizen burst. Remember in the symbols that we talked about for general symbols, the Kaizen burst symbol? Yeah, we point out opportunities again using the Kaizen burst symbol. Establishing the scheduling methods. Kanban and direct links now schedule all operations short-term. Both the work cell and the supplier, however, need forecasts to plan staffing and possible changes in inventory levels. The map here shows this monthly information flow. So we work with the customer based on the demand. We ask that the customer provides us 3-month forecast with monthly blanket order. Then we communicated the 3-month forecast updated monthly that is aligned with customer and monthly blanket order. Again, as you can see how the orders, right, customer and the suppliers are kind of identical. So the purchasing here must arrange for payment. They intend to do so with a monthly blanket orders, and as you've seen them here. So the next one is calculating the lead and cycle times now based on the new opportunities. So when we reduce the inventory or lot size from 1,000 down to 250, now we are, as you can see here, our inventory level is reduced. Sorry, this was actually shipping receiving frequency, so half day. And then the lot size is 2.5 days. And then now that, they're utilizing the cellular manufacturing concept, we have combined all that into one cell with only 2 operators. Takes 129 seconds. Then we also reduced the lead inventory size after. So at the end of the day, we have a new process time of 129 seconds, which didn't change, but then the lead time overall went from 41 days down to 5 days. That's, again, now this is this is your future state, and you take this information. Of course, in order for you to proceed and get get this project work going, you need approval from management. And this is the best way. This is your final product of VSM to present to your management team and ask for support. And again, if you can compare before and after here, so 36 days less inventory to me would trigger a lot of attention. So some key takeaways. So VSM will reduce lead time, as you already saw that, will increase the value added time and decreasing non-value added time, as you already witnessed through lead time. Reduce cost. So we went from 4.1 person down to only 2 operators, only on the labor side of it. We had also accomplished setup reduction. That's also cost reduction opportunity there. And not to mention the inventory cost, right? That was reduced drastically. Improved decision-making process, as I pointed out, that final product, the future state of VSM, is going to improve the decision-making, right? So and the next one, help to see the sources of waste in the value stream. That's also a key point on this. Provides a common language. So why I'm pointing this out, because again, through this common language, whoever you work with, everybody understands the meaning of your map. Next one is makes decisions about the flow. Remember, information and the material flow apparent. Ties together Kaizen concepts and techniques. Forms the basis of an implementation plan. There is also the linkage between the information flow and the material flow. And finally, provide a way for employees to identify and eliminate areas of waste.